In the last section, we talked about angle and side relationships in isosceles and equilateral triangles. Now we're just going to talk about any kind of triangle, and we're going to continue to talk about some angle and side relationships. So no matter what kind of triangle you have, there's a relationship that says the longest side and the largest angle are going to be opposite each other. And so in this picture that's kind of reddish here, this is the largest angle, right? That's an obtuse angle, and that's clearly bigger than the other two angles. If you go directly across from that angle, you'll be hitting the largest side. So that's one relationship. And of course, if you think about that with the shortest side, that's also going to be true. So the shortest side and the smallest angle are going to be opposite each other. So in this bluish picture, if we find the shortest or the smallest angle, which would be this one right here, that's tinier than anybody else, and you go opposite that, you will bump into the shortest side. So sides and angles have that relationship inside of a triangle. The longest side will be opposite the largest angle, and the shortest side will be across from the smallest angle. So what we can do with that information is we could order the sides of a triangle from smallest to largest, like they're asking us to do in example 1, based strictly on the angle measurements. So we can order the sides if we know something about the angles. So they're asking us to go from smallest to largest. So if we look at the smallest angle, which is 51 degrees, and we go opposite that, we will be bumping into the smallest side. And so the smallest side is going to be side AB. If we find the next smallest number, we're going to be looking at 62. We go across from that, we'll be bumping into side BC. So that would be the next largest side. And then the largest side, sorry about that. The largest side will be across from the 67 because the 67 is the biggest angle. So if you go across from that, you'll be bumping into the longest side, which is AC. All right, so that's how that works. Now in example B, first of all, we're communicating with the symbol here, so we should know that angle F is 90 degrees, right? And also one of the angles is missing. So we would need to figure out what is angle D before we could start ordering the sides from smallest to largest. And so you would just take 180 minus 90 minus 33, and you would get 57 degrees. So this angle inside here is 57 degrees. Let's do that a little differently here. Okay, now that we know the measurements of all three angles, now we could order them from smallest to the sides from smallest to largest. So again, find that smallest angle, 33, 57, and 90. The smallest number there is a 33. Go opposite that 33, and you've just bumped into the smallest side. So I'm going to call that DF. Remember what we learned in chapter 1. If you want to call that FD and switch the order, that would be completely fine. It doesn't matter which order you say the letters in. FD, DF, same thing. All right, the next biggest number is a 57. So if we go across from that, we bump into FG. And then finally, the biggest number in this triangle is a 90. So if we go across from that, we bump into DG. Right? So that's the sides ordered from smallest to largest. Not really sure why I felt the need to do one more, but really driving home the point that you have to know all three angles, right? If you don't know the missing angle, you've got to figure it out. So 180 minus 127 minus 29 is going to give you 33 degrees for this missing angle. And so now that we have the information about all, I'm wrong. I'm sorry. I'm just looking at my calculator here. It's 24, not 33. I thought I remembered correctly. It's not. Sorry, it's 24 degrees. All right, now that we have information about all three angles, we could start to order the sides. So if we pick the smallest angle and go across from that, we're going to get NP. The next smallest side is 29, next smallest angle is 29. If you go across from that, you bump into MN. And then finally, that largest angle, that obtuse angle, if you go across from there, you'll bump into MP. And hopefully in the last two examples, you see that 90 and that 127, and you realize, of course, the longest side is going to be across from those angles, because you can only have one right angle or one obtuse angle in any triangle, and the other two angles are definitely going to be smaller than those. So if I asked you what the longest side was, hopefully the minute you saw the 90 and the 127, you'd know to go across from those. All right. So when we were given angle measurements, we could figure out some information about the side lengths. All we really could do is order them. We don't know what length they're going to be, but we know which one's biggest and which one's smallest and which one's in the middle. So the same is true if we want to work that idea backwards. If instead we know something about the sides, then we can go opposite the side to get to the angle. So the 10, if we go opposite the 10, we're going to have a T. If we go opposite the 6, we're going to have an S. And if we go opposite the 9, we're going to have an R. So this time they want us to go smallest to largest, and they want us to order the angles. So the smallest was the 6. When we went across from the 6, we bumped into angle S. The next biggest number is a 9. When we went across from the 9, we bumped into angle R. And then 10 is the biggest side length, so when we went across from the 10, we bumped into angle T. So if we go opposite the biggest side, we'll hit the biggest angle. If we go across from the smallest side, we'll hit the smallest angle, and then of course we can do the middle one too. All right, one more time here. Let's try one more time. Again, we go smallest, which is that 13, right? If we go across from the 13, we're going to bump into angle J. The next biggest number is 25. If we go across from that, we bump into angle K. And then finally, we have a 28. If we go across from that, we have angle L. And we have now ordered the angles based on information about the sides. All right, so that's what we could do with that first it doesn't really say it's a theorem. I guess it's just kind of a fact up there that the longest side is across from the longest angle, and the smallest side is going to be across from the smallest angle. So we could order the sides and angles using that information. All right, a completely separate theorem. This one says that a certain relationship must exist among the lengths of a triangle in order to form a triangle. So not every set of segments could actually form a triangle. So if you look at that top picture, it's saying if you have a 4, and a 7, you could actually build a triangle. You could put those three side lengths together and they would form a triangle. And I don't know what the units are. Maybe it's inches, maybe it's centimeters, but no matter what the units are, if there was a 4, and a 7, you could build a triangle. Whereas if you had a 3, and a 7, you could not build a triangle. You wouldn't get those sides to meet up. And if you think about that, 3 and 3 don't even make 7, right? Those two smaller sides don't have enough to form a peak. They're not long enough. They're not even bigger than 7. So how could they form a peak? So there's this relationship that we talk about. It's called the Triangle Inequality Theorem that's supposed to help you know whether or not you could form a triangle. So let's label our sides. Our angles are A, B, and C, but let's label our sides. And they typically label our sides with lowercase letters. Remember, uppercase letters are for points, so all of our sides meet at these individual points here, or vertices, and so those get capital letters. So if we go across from A, we'll label that with a little a. If we go across from B, we'll give that a little b, and across from capital C, we'll give a little c. And that would be a standard practice to label your sides with lowercase letters and your, of course, your vertices with uppercase letters. And so the Triangle Inequality Theorem says, if you add any two sides, it needs to be bigger than the third. So if I take A plus B, side A plus side B, so again, I don't know, maybe they're 3 inches and 5 inches. As long as that sum is greater than the third side, you'd be able to form that peak that you need to make a triangle. Now, it doesn't have to be sides A and B. What if you add up sides B and C? B and C have to be bigger than A. So any two sides you pick, when you add them up, that sum needs to be bigger than the third side. And of course, maybe we want to add up A and C instead. Well, those two, if you add them up, have to be bigger than B. So all three of these need to be true in order to form a triangle. However, there is a shortcut. But the shortcut is, as long as the two smaller sides add up to something bigger than the biggest side, then you are definitely going to be able to form a triangle. So we really don't have to perform all of these three tests. We can do this shortcut down here. Again, and the shortcut says the sum of the two smaller sides has to be bigger than the biggest side. So it must be greater than the longest side. So rather than performing those three tests that were up above, the shortcut would be, as long as you sum up the two smaller sides and it's bigger than the longest side, then you will be able to form a triangle because the other two relationships will automatically be true. So what that means, in example 3, says, can you form a triangle? Tell whether a triangle can have sides with the given lengths. Would you be able to form a triangle with these three lengths? So take the two smaller numbers, which are 3 and 5, so add them up. Is that sum greater than the longest side, which is 7? And so ask yourself, is 8 greater than 7? And the answer is yes. Therefore, the answer is yes to the question of, can you form a triangle? Yes, you can form a triangle. Now, don't be fooled if the numbers are not in numerical order. So don't just add the 4 and the 11. Add the two smaller numbers, which is the 4 and the 5. That has to be greater than the longest side. So don't just pick the first two numbers you see. Pick the two smaller numbers and add them up. And this says 9, is 9 greater than 11? And no, it's not. So this answer to the question is no. You could not form a triangle with a side length of 4, 11, and 5. And again, maybe it's inches, maybe it's centimeters. I really don't know what the units would be. All right, so that's a second little theorem that we have in this section. The final theorem says, what if we only give you two sides? If I give you the lengths of two sides, what's the possible length for the third side? And if you think about that, if you have two sides, let's say one of them is maybe 10 and one of them is 2. We'll make a small one and a big one. If you put them together at kind of a bigger angle, notice I formed kind of a large angle there. The third side that you're going to add in, this green one, how big does it have? How big could it be? So I could put the 10 and 2 like that with kind of a bigger angle, or I could take the 10 and 2 and put them like that at a little angle, right? I don't have to go greater than 90. I could go less than 90. And in that case, the distance, this green distance, is going to be even shorter. And so we want to ask ourselves, if I only know 2 of the side lengths, what range of possibilities is there for that third side? And so the way you do that, the test or the calculation you perform is take the difference of the two numbers. So take the difference of the two known sides and take the sum of the two known sides. And those will be your upper and lower bounds for the third side. So the third side has to be somewhere in between. So the range for the third side, all right, let's just write third side in there, has to be somewhere between the sum and difference of the two known sides. So what that would look like in example 4, we know one side is 12 and one side is 8. So if we take a 12 minus 8, we get 4. That'll be our lower bound for our third side. If we take 12 plus 8, we get 20. That'll be the upper bound for the third side. So our third side has to be somewhere between 4 and 20. So those are your 3 facts about triangles for today.